So this is a quick video to walk through how to solve this proton NMR spectrum. So we have the molecular formula here. So we have C3H8O. And so what I'm going to do is kind of go through and assign each individual peak and then kind of check off, the carbons, hydrogens, and oxygens as they appear. And that will, again, help me to limit the overall possibilities that are occurring. So probably the best place to start is the furthest upfield, so the closest to zero in our proton NMR spectrum. The reason for this is typically a region that does not, it's not adjacent to a variety of functional groups. And one of the key pieces that we frequently see in our proton NMR spectrum is a signal that has 3. So this integration of 3 is very key here because ultimately this tells me that I have 3 hydrogens. So I am at the end of my molecule. So again, this is a good reason why we start at this position, because we're going to kind of start at the end and then work our way over to that functional group. So I have an integration of 3, and I'm going to take a look at the shape of my peak. So I notice that I have 1, sort of 2, and 3 peaks within that particular signal. So that is what we would call a triplet. So a triplet with an integration of 3 is going to be a CH3 that is adjacent to a CH2. So these 3 hydrogens here, again, the integration of 3, so it tells me there's 3 in that particular signal, and then it's next to 2 adjacent hydrogens. So it sees the 2 hydrogens here plus 1, that's going to give me my triplet. And so we'll frequently see this peak that is a triplet with an integration of 3, and again, that's what we'd call our terminal CH3. Next, I'm going to take a look at the sextet. So what this sextet is telling me that this signal sees, so it sees 5 overall hydrogens. And actually, before we move on, what I want to do is, again, limit the number of carbons and hydrogens that I have. So I've already assigned the sort of partial structure for CH3. So now I have 2 carbons to deal with, and then I have 5 hydrogens remaining, and my still 1 oxygen remaining. Okay, so again, it's important for us to keep track of what we have. So this is going to see 5 hydrogens, but based on what we've talked about in organic chemistry, I can't have a carbon that has 5 hydrogens. That's just, it violates the valency of carbon. Again, carbon can bond up to 4 different things. So this is going to come from 2 different environments. So I know that I already have a CH3 here, so that is essentially 3 of the protons that it sees. And then it's going to see 2 hydrogens on the other side that will get me to 5. So what I know now is that it is a CH2, again, based on the integration. So there's 2 hydrogens in that signal. It's going to see 3 on one side and 2 on the other. 3 protons on one side, 2 on the other side. Okay, so the partial structure is going to look like this. Again, if I take a look at this set of hydrogens here, it sees 2 hydrogens on this carbon here. So there's 2 hydrogens on this carbon, and there's 3 hydrogens on this carbon. So it sees 5 altogether plus 1. That gives me my sextet. Okay. So with that, I have now taken into account the carbon and 2 protons here. So that's another part of my partial structure. So I've really accounted for that. So I have 1 carbon remaining, and I have technically 3 hydrogens remaining. So I know based on this partial structure that I've drawn, I actually have a carbon atom at this position here with 2 additional hydrogens, okay? So that is where my last carbon is and my 2 hydrogens that are remaining. So in reality, I just have 1 hydrogen left to assign. And if I take a look at the shape of the signal corresponding to the peak at 2.26, that is going to be a singlet, right? There's only 1 sort of individual peak that I see for that given signal. And it is a little bit broader than our traditional signals. So again, if you look kind of at the bottom of the signal, if we look at the bottom of the signal, it's a little bit broader than we would normally see with a sharp singlet. So this is going to correspond to an alcohol. Again, remember that I have this CH2 remaining. That's ultimately going to be this partial structure up here. So all I have remaining is an O and an H, and that corresponds well with a singlet with an integration of 1. So that's going to be my alcohol peak. Again, remember that my alcohol proton does not see the 2 hydrogens that are here. So it does not see the 2 hydrogens at this position here. So ultimately, it's not split by these 2 hydrogens. And also, when we take a look at the partial structure up here as well, again, this is what we would define as a triplet. So it's 1, 2, and 3 peaks for that particular signal. So Again, when we take a look at this signal here, again, has an integration of 2. So there's 2 protons in that particular signal. If we look to the right, it does not see this hydrogen, right? In the same way that this is a singlet, the coupling or the splitting is reciprocal between the CH2 and the OH. So they don't see each other. So it's not split to the right. However, there are 2 hydrogens on this signal here. So it sees the 2 hydrogens on this left. So 2 plus 1 is going to get me to my triplet, and this has an integration of 2. So if I put all of these partial structures together, I get this alcohol as my final product. So again, I have an alcohol on one end, a CH3, and then 2 CH2s in the middle. Another thing to point out here is that the chemical shift of these 2 protons here, adjacent to the alcohol, are the ones that are shifted the most downfield. So it has the highest value in the x-axis, and again, that's because it is the closest to our functional group, to our OH.